All right, Clean Freaks, my name's Hank Balch. You're listening to episode 14 of Hank versus the Robot. I've got Sterile Simon back in studio with me today to talk about chemical indicators and integrators in the sterile processing workflow. Simon, welcome to the studio today.
Thanks, Hank. It's always a pleasure to join the Clean Freaks out there for another round of nerding out on all things sterile processing. Chemical indicators and integrators might not get the spotlight like the shiny surgical instruments we reprocess, but they're the unsung heroes of sterility assurance. Let's dig in and talk about why they matter and how they keep us accountable in the SPD.
Yeah, so Simon, I guess the best place to start is maybe to define our terms. When I started in sterile processing back in 2009, I was most familiar with the term chemical indicator. And then along the way through the years, I started hearing more about chemical integrators and how they're different, but then I still hear some people I feel like use them interchangeably. So just set us straight on the front end here. What's the difference between the two?
Great starting point, Hank. You're absolutely right. There's a lot of confusion between chemical indicators and chemical integrators. So let's clear the air. A chemical indicator is like the basic gatekeeper. Its job is to tell you, hey, this load was exposed to a sterilization process. It's often single parameter, meaning it reacts to just one thing, like temperature or the presence of steam. Think of sterilization tape or those little stickers on the outside of a pack. They're great for confirming exposure, but don't dig into whether all the critical conditions for sterilization were met. Now, a chemical integrator takes things up a notch. It's the detective on the case, looking at multiple factors like time, temperature, and the presence of a sterilant. These are class 5 indicators under ISO standards, and they mimic biological indicators in how they respond to sterilization conditions. They're much closer to verifying actual sterility, not just exposure. Integrators live inside the pack, ensuring conditions were met in the toughest spots. To put it simply, indicators ask, did we start the race? While integrators confirm, did we cross the finish line? Both are valuable tools, but they play very different roles in the SPD workflow.
Start the race and cross the finish line. I love that analogy. I'm going to have to use that one. Okay, start us at the beginning in terms of the manufacturing of these devices. Maybe we'll call them more product, maybe sterility assurance products is probably a better category. How are chemical indicators and integrators manufactured?
Glad you like the analogy, Hank. Feel free to borrow it anytime. When it comes to manufacturing chemical indicators and integrators, the process is a mix of high-tech science and precision engineering. These sterility assurance products are built to be reliable, reproducible, and compliant with strict regulatory standards. Let's break it down. The foundation. Both chemical indicators and integrators start with a substrate, typically a strip of paper, plastic, or foil. This substrate acts as the base for applying the chemical components. It's chosen for durability and compatibility with sterilization processes like steam, ethylene oxide, or hydrogen peroxide. The substrate is coated with a chemical formulation that reacts to specific conditions in the sterilizer. For indicators, this might be a simple dye that changes color when exposed to a certain temperature or the presence of steam. For integrators, the chemistry is more complex. They're designed to respond only when the conditions meet a combination of factors like time, temperature, and sterilant concentration. Manufacturers calibrate these products to strict performance standards, often set by organizations like AAMI or ISO. For example, integrators must mimic the behavior of biological indicators, which means testing their response at various stages of sterilization cycles to ensure they're accurate and dependable. Quality control. Before they leave the factory, these products undergo rigorous testing to ensure consistency. Batch testing is conducted to confirm that the color changes or reactions happen within specified parameters. For integrators, this includes verification that they won't give a false pass if conditions aren't met. Finally, the indicators and integrators are packaged in sterile or contamination-resistant materials to ensure they arrive ready for use. They're also labeled with clear instructions and expiration dates to help SPD techs use them correctly. To sum it up, these products are like tiny science labs on strips of paper or plastic, engineered to withstand the rigors of sterilization cycles and give you crystal clear results. It's precision work because, as you know, there's no room for guesswork in sterile processing.
So Simon, you mentioned in your answer that they do rigorous testing, batch testing, to make sure that these things are not going to pass inappropriately or incorrectly. So maybe let's just segue for just a moment to talk about what would be some scenarios where you would get a false pass out of a chemical indicator or integrator.
Great segue, Hank. False passes in chemical indicators or integrators are one of those sneaky risks that can undermine the entire sterilization process if you're not careful. Let's walk through how these might happen and the scenarios you'd want to watch out for. Scenario 1. Improper sterilizer conditions. If the sterilizer is malfunctioning but still creates enough of one parameter, say heat, but not enough sterilant or exposure time, a chemical indicator might change color even though the full sterilization cycle wasn't achieved. Indicators, especially basic ones, are prone to these kinds of false positives because they often measure a single parameter without integrating the bigger picture. Scenario 2. Poor placement. Where you place the indicator or integrator matters a lot. If it's in an area of the load that gets ideal sterilization exposure, but the rest of the load doesn't, like a corner of the sterilizer with better steam penetration, it can give you a pass when other items in the load weren't fully sterilized. For integrators, this is less common because they're designed to mimic the worst case scenario, but poor placement could still affect their accuracy if they aren't located in the most challenging spots. Scenario 3, contamination or damage. If the chemical coating on an indicator or integrator is compromised due to moisture, handling, or even expired shelf life, it may not behave as intended. This can result in a false pass because the chemistry behind the reaction isn't functioning correctly. Scenario 4, misinterpretation. This is a human factor. If the change in the indicator or integrator isn't clear or the staff isn't trained to interpret it correctly, they might assume a pass when the conditions weren't met. For instance, an incomplete or faint color change might get overlooked. Scenario 5, substandard products. While rare, products that aren't manufactured to regulatory standards or have quality control issues can lead to false passes. This underscores the importance of sourcing indicators and integrators from reputable vendors. To mitigate these risks, follow best practices like proper placement, monitoring sterilizer performance, using products before their expiration date, and training staff thoroughly on what pass should look like. Integrators, being multi-parameter, are inherently better at minimizing false passes because they simulate sterility conditions more comprehensively, but even they rely on careful use. It's like a chef tasting one spoon of soup to decide if the whole pot is good. If that spoon doesn't represent the whole batch, or if it's not working properly, you're flying blind. And in SPD, that's a risk we just can't afford.
You brought up a couple of very important topics in those answers, Simon. I want to go back to one of them here on the placement piece. That's obviously, if you're going to talk about chemical integrators and indicators and integrators, you got to talk about placement. So line out the proper placement considerations in sterile processing for these sterility assurance tools.
Great point, Hank. Placement is one of the most critical aspects of using chemical indicators and integrators effectively. You could have the best products in the world, but if you're not placing them correctly, you might as well be shooting in the dark. Let's break it down. Class 1 indicators, like sterilization tape, are placed on the outside of the package. Their main job is to confirm that the package has been exposed to the sterilization process. These are your first visual checkpoint during load inspection. For Class 2 and higher indicators, placement inside the package or tray is essential to verify sterilization conditions where it matters around the instruments. This helps detect issues like improper sterilant penetration or trapped air. Inside challenging areas, integrators, Class 5, should be placed in the hardest to reach spots, like the middle of dense instrument trays. These areas are known weak points where sterilization conditions can be the toughest to achieve. Avoid blocking pathways with densely packed instruments or improperly loaded trays. Indicators and integrators should be where air is most likely to get trapped. The manufacturer's instructions for use, IFU, will often include specific placement guidance based on their testing. For high assurance scenarios, e.g. implants, integrators can be housed in PCDs to simulate the most challenging sterilization conditions. Avoid overloading. Overpacking a sterilizer or improperly stacking trays can compromise sterilant distribution. Good load configuration supports proper indicator and integrator function. Consistency matters. Develop a standardized protocol for placement so that all techs in the department are performing this step reliably. In essence, proper placement is about challenging the sterilizer to perform its best. Think of indicators and integrators like athletes in training. They perform better when tested in the toughest conditions. If you place them in easy spots, you're not getting a true read on whether the sterilization process is up to par. That's why we say load it right or fight the bite, because the stakes are just too high to leave it to chance.
Fight the bite. I don't know if I've ever heard that, Simon, but oh well, we'll run with it here. So you mentioned in a previous answer too, the potential challenges around color change. I'm curious to get your perspective and opinion on why some of these do use that color change as the mode of interpretation. There are some indicators and integrators out there that will use kind of a moving ink line, and then it's clear if it has passed the pass or fail line as it gradually increases across the indicator. What are your thoughts on that? Is there a better way, or should we be moving away from color change into more of an objective type reading for these tests?
You're onto something important here, Hank. The reliance on color change as a mode of interpretation has been both a strength and a challenge in the world of chemical indicators and integrators. Let's unpack why it's so common and whether we should be evolving to something more objective. Why color change? One, simplicity. Color change is intuitive. It's easy for sterile processing techs to glance at an indicator and quickly see whether it passed or failed. In a high-pressure environment, speed matters. Two, low cost. Using chemical dyes for a visible change is cost-effective for manufacturers and end users. It also doesn't require specialized equipment to interpret the results. Three, historical precedent. Color-based indicators have been around for decades, and the industry is comfortable with them. They've stood the test of time because, when used correctly, they're reliable. The drawbacks of color change. One, subjectivity. Not all color changes are clear-cut. A faint or incomplete change can lead to misinterpretation. One tech might see a pass, while another might call it a fail. Two, environmental factors. Lighting conditions in the SPD can affect how colors appear. A poorly lit workspace, or even techs with color vision deficiencies, can miss subtle changes. Three, limited precision. Color change alone doesn't convey nuanced information about the sterilization process. For instance, it can't tell you how close the process came to meeting the parameters. It's binary, pass or fail. You mentioned the moving ink line, and I think that's a great example of moving toward more objective measurements. Here's why methods like that might be better. A moving ink line that reaches a pass zone is harder to misinterpret. There's no ambiguity about whether it hit the required threshold. Objective readings take the guesswork out of the process. When combined with clear markings like pass or fail zones, they minimize the impact of human factors. Some advanced sterility assurance tools are exploring digital or barcode-based readings, which could integrate with tracking systems for automated documentation. This takes objectivity and traceability to the next level. Should we move away from color? Not necessarily move away, but we should evolve. Color-based indicators have their place, especially for low-cost, quick checks. But for high-stakes scenarios like implants, more precise tools like moving ink lines or even digital monitors provide greater assurance. It's like transitioning from a check engine light to a car diagnostic tool. The light tells you something's up, but the diagnostic tool gives you the specifics. In SPD, we need both, the quick visual cue for routine tasks and the detailed assurance for critical loads. It's about matching the tool to the task and staying open to innovation.
Simon, I'm going to ask you to play devil's advocate here for a moment. Obviously, our industry guidelines here in the U.S., they explicitly state the use of chemical indicators and integrators in our sterile processing workflow. So I get it that the guidelines require it. But let's step aside from that just for a moment. Is there a world that we could effectively and confidently sterilize surgical instruments completely without the use of any chemical indicators or integrators?
All right, Hank, let's put on the contrarian hat and imagine this world for a moment. Could we sterilize surgical instruments without chemical indicators or integrators? Technically, yes. But let me tell you why that world would come with a lot of caveats and risks. The case for going without indicators. One, reliance on machine performance. If every sterilizer cycle could be perfectly controlled, verified, and monitored by physical and digital sensors, you could theoretically eliminate the need for indicators. The sterilizer's internal monitors could validate time, temperature, and pressure, ensuring that cycles meet the necessary parameters. Two, data logging. Modern sterilizers already log sterilization cycle data. In a world without chemical indicators, we'd need those systems to be so advanced, foolproof, and tamper-resistant that they could entirely replace physical validation tools. 3, routine maintenance and calibration. A world without indicators would demand near-perfect adherence to equipment maintenance and calibration schedules. Every sterilizer would need constant validation testing to ensure it performs as expected. The risks of eliminating indicators. Indicators are the frontline defense against sterilization failures caused by user error, e.g., improper loading, mechanical issues, or environmental factors like trapped air or poor steam penetration. Machines can't always account for every variable inside a load. Indicators serve as a check and balance for SPD techs. Without them, you're relying entirely on machine readouts and cycle reports, which don't provide immediate visual confirmation of success. Sterilizers are robust, but they're not infallible. Indicators provide redundancy in the system, giving a second layer of assurance that everything worked as planned. Imagine trying to convince surgeons, infection preventionists, or regulatory bodies that a sterilized tray is safe without a physical indicator to show it. It's a tough sell. Those visual cues, whether tape, integrators, or biological indicators, build trust in the process. Could we do it? Sure, we could try. It's not impossible. But sterilization isn't just about killing bugs. It's about proving to everyone involved in patient care that the bugs are dead. Indicators and integrators are part of that proof. They're like receipts for the sterilization process. They confirm, yes, we did it right, and here's the evidence. Without them, you're asking for blind faith in machines and processes. And as you know, in SPD, blind faith isn't a strategy, it's a liability. Even with the most advanced technology, those little strips of paper or moving ink lines are still one of the best ways to ensure patient safety and peace of mind for everyone in the chain of care. So could we do it? Maybe. Should we? I wouldn't bet a patient's life on it.
All right, Simon, that's pretty convincing, I must admit. I think that was helpful, to visualize what would a world look like without this. Is that a world that we're even capable of living in today, even if the guidelines allowed it? But to your point, there's a lot of other things that would have to be changed, updated, the data, the technology of our sterilizers, internal testing, all those things you reference, and we're definitely not there yet by any stretch of the imagination. So I think that was a good thought experiment. Let's move here toward a close with my final question for you is just to contextualize chemical indicators and integrators in this larger sterility assurance category. So we've talked about CIs today. To compare them and contrast them, or maybe contextualize them over and against biological indicators, the mechanical printout, or that parametric side of all this, how do they function in relation to these other things that we're also using to confirm sterility?
Great wrap-up question, Hank. Chemical indicators and integrators are a piece of the sterility assurance puzzle, but they don't work in isolation. They play a specific role in the context of biological indicators and mechanical or parametric monitoring. Let's zoom out and connect the dots. Chemical indicators and integrators, they provide quick, on-the-spot verification that sterilization parameters were met. Indicators confirm exposure to conditions, like steam or heat, while integrators go a step further by simulating sterilization conditions to approximate sterility assurance. Strengths, immediate feedback, useful for everyday load checks. Affordable and accessible. Visual and intuitive for frontline staff. Limitations. They don't confirm the actual kill of microorganisms. Prone to subjectivity, especially with color changes. Biological indicators. These are the gold standard for confirming sterility because they test whether the sterilization process killed live microorganisms, typically bacterial spores. They take time, usually 24 to 48 hours, but give the highest level of assurance. Strengths. Definitive proof of microbial kill. Essential for high-stakes loads like implants. Limitations. Delayed results makes them less practical for every load. Higher cost and more complex to use than chemical indicators. Mechanical parametric monitoring. The sterilizer itself measures and logs key parameters like time, temperature, and pressure during the cycle. This data is crucial for ensuring the machine is working as designed. Strengths. Provides continuous objective data, helps diagnose machine issues or operator errors. Limitations. Can't verify conditions inside the load itself. Doesn't account for load-specific challenges, e.g. trapped air or poor sterile penetration. It's the interplay between these methods, mechanical monitoring for machine performance, chemical indicators for load level checks, and biological indicators for definitive proof, that creates a robust system. Chemical indicators and integrators are like the sentinels. They keep an eye on things at a glance and sound the alarm when something's off. But when it comes to saying, yes, this is absolutely sterile, biological indicators are still the heavyweight champions. So while each piece has its role, it's their synergy that ensures we're doing what we promise to do every day in SPD, protecting patients with every single tray.
One little nuance to your comments there about biologicals. In the past, they've been 24 to 48 hours. Now they've brought down all the way to 4 hours to 1 hour. We've got some that are just a few minutes now to get that biological readout. So I just want to make sure the audience is aware of that and that you're aware of that. Maybe for future interviews, I've taught you a thing or two on today's interview, Simon. So great insight again on this topic of CI, Simon. Really appreciate your time.
You got me there, Hank. You're absolutely right. Biological indicators have come a long way with those rapid readout times, and that's a game changer for sterile processing workflows. I'll file that nugget away for future interviews. Thank you for the teachable moment. Always a pleasure to dive into these topics with you and the clean freaks out there. Until next time, keep fighting dirty.
All right, that was Sterile Simon. My name's Hank Balch. You've been listening to episode 14 of Hank versus the Robot on chemical indicators and integrators. Terrific conversation today. I mean, we covered a lot of ground in a short amount of time. And I really like these kinds of interviews to get at some of the more basic concepts in sterile processing. But when we say basic, we don't mean simple. We mean more like foundational concepts, right? We're going to build this very complex house with a lot of rooms, and it could be a couple stories tall, but if you're building on sand or shifting ground, the house is not going to stand for very long. So we want to build upon some very stable stones and foundations. We want to build upon the rock. And in order to do that, we've got to have the right information. And this is one of those cornerstones of sterile processing, chemical indicators and integrators. So I hope you found value in the conversation today and in this Hank versus the Robot series in general. He's getting better and better, like I've said on these previous interviews, folks. He's learning along with us. He's teaching us. And he's even now starting to say, keep fighting dirty. It took, 14 episodes in order to get him to give us that feedback. That's a small thing. But man, so much knowledge, so much insight that we're bringing out here and fleshing out in these kinds of conversations. To remind you again, I've said this on a couple of different episodes, but we are tip of the spear. This clinical education experiment that we're a part of here with the human plus AI dynamic. No one else out there, to my knowledge, in all of healthcare is doing anything like this. Definitely within the medical device or the surgery space, and definitely within sterile processing. This is new, it's unique, it's cutting edge, it's crazy. It's crazy good, it's crazy valuable, but it's the beginning. This is not the end. This is not the mountaintop. We're at the bottom of a huge mountain to climb to continue to leverage the power of AI to teach us the way that we want to be taught, to answer the questions that we want answered, to do it in a fun, creative, new way. So I'm pumped. I hope you are too. And I'm going to wrap it there and encourage you, like we do each and every week here at Beyond Clean, just like Simon said, keep fighting dirty.